Hello, I'm Ryan Kinchin with High Desert Math Tutor, and today I want to talk to you about vertical asymptotes and holes. So, vertical asymptotes and holes both occur at x values that would cause the denominator of a rational function or an expression to become 0. So, the denominator is the part of this function that could be problematic. Now, before we get into asymptotes or holes any further, let's go ahead and figure out what x values we have to avoid plugging into this function. Now, we do that by factoring the numerator and the denominator of any rational functions we have. So, for the numerator, we see there's a common factor of 3. So we factor this to be 3 times x minus 1. For the denominator, we do a little thinking here. It looks like we can factor this into x plus 2 and x minus 1. So right here, in this form, we can see the two factors that are being multiplied to give us this denominator. Now, to figure out what x values are restricted, what x values we are not allowed to use in this function, we can set each of these factors equal to 0. So what we're going to say is x plus 2, I'm going to do something better. I'm going to say that is not allowed to equal 0. Because if this factor equals 0, then 0 times anything becomes 0. Separately, we'll take this factor, x minus 1, and we're going to say that is not allowed to equal 0. And now, just like any typical fashion, we can solve both of these equations. So subtract 2 from both sides, then we get x is not allowed to equal negative 2. Over here, we add 1 to both sides. We'll cancel this out, and we see that x is not allowed to equal positive 1. So if we let this function, or if we plug it into this function, the x value negative 2, or the x value positive 1, that would cause the denominator to become 0. That means we'd be dividing by 0, which you can never do in math. So we know right now, these are two x values that we absolutely have to avoid. Now, let's quickly revisit this definition, the beginning of the definition for vertical asymptotes and holes. Vertical asymptotes and holes both occur at x values that have the potential to cause the denominator of this expression to become 0. So let's dive into this more deeply. Now, we see this function has a common factor in the numerator and the denominator. So and typically we want to cancel those common factors so that we can obtain a simpler function. When we do this, our simplest version of this rational expression is 3 divided by x plus 2. Now let's get into vertical asymptotes. Vertical asymptotes occur whenever you have factors in the denominator that have the potential to become 0, but you are not able to fully cancel those factors from the denominator. So you see this denominator? We have x plus 2. We could potentially plug in negative 2 for this x value, and that would make the whole denominator become 0. Now, see, there's no x plus 2 in the numerator. We can't cancel this factor. So we're stuck with x plus 2 in the denominator, which means we can never plug in negative 2, but also that means that this gives us what we call a vertical asymptote. So if we look over here momentarily, so the function we have is f of x. The blue graphs right here, that is what makes up the graph of f of x. So we see that this denominator would become 0 if we make this x -2. But again, remember, we're not allowed to make x equal -2. So if we look over here, when x is -2, we have this vertical dashed line. That's what we call a vertical asymptote. So let me just pencil that in. That is our vertical asymptote. So vertical asymptotes, you can never cross this vertical asymptote without having to split your function into more than one piece. See, this blue and this blue, that makes up the graph of f of x, but we had to split this into two pieces because we cannot continuously cross this vertical asymptote. Because if we were to cross it without jumping, that means there would be a place where x is equal to -2, but x cannot equal -2. So once again, vertical asymptotes occur for functions and expressions when you try to simplify this expression as much as possible. You cancel any factors you can possibly cancel, and you still have factors in the denominator that have the potential to become 0, to make the whole denominator become 0. These factors are the ones that give you vertical asymptotes. Now, in a problem, we would state a vertical asymptote by giving the x value where the vertical asymptote occurs. So over here, I'm going to state our answer. So for this expression right here, for this graph, we can see the vertical asymptote occurs when x is equal to -2. That's the equation that describes the vertical asymptote. Okay. Now moving on to holes. Holes occur when you have factors in the denominator that have the potential to make the denominator become 0, but you are able to fully cancel those factors from the denominator. So notice we have an x minus 1, x minus 1. This factor of x minus 1 in the denominator could make the denominator equal 0. But right here, we actually managed to cancel those factors completely, so there's no more x minus 1 in the denominator. So the fact that we got rid of that x minus 1 allows us to get a better graph for the function that does not have a vertical asymptote. But that doesn't change the fact that x is not allowed to equal positive 1. Because if x was positive 1, that would make this factor 0 in the original function. So the denominator of the original function would become 0. So we have to skip over this x value. So we can come over here and look at our graph. When x is equal to 1, you have to look nice and close, but there's a little hole right there. The graph comes down nice and smoothly, and right where x would be equal to 1, we skip over that exact point, and then we continue on. Holes occur, again, at x values that would cause the denominator to equal 0, but you were able to cancel out that factor in the denominator, so it's no longer there. So when we state holes in answers for problems, in problems you want to state the holes as an ordered pair where you include the x value or the x coordinate and the y coordinate of where this hole resides. So what we can do here, we remember in this original function we're not allowed to plug in x equals 1. Since we were able to sort of transform or simplify this function into a simpler version, this particular version we are allowed to plug x equals 1 into. But just remember, for the original, we're not. So to figure out what y value this hole resides at, what we'll do is we'll take the simpler version of this function and we're going to plug in the x value of the whole with the simpler version of the function. So we take our 3 over 1 for our x value plus 2. That gives us 3 divided by 3, which is 1. So in our final answer for the wholes, we are going to give the ordered pair. The x value of the whole is at 1, and the y value of the whole is also at 1. So there you go. This is what your teachers would expect to see when you are supposed to give them the vertical asymptotes and the wholes for a function or an expression. Now, just a quick recap, because this idea, many people can process it, but then there's a lot of information to remember. So I want to just recap one more time. Vertical asymptotes and wholes have one thing in common. They both occur at x values that would cause the denominator of some expression or function to become 0. That's what they have in common. But where they diverge, what makes vertical asymptotes different from wholes is that vertical asymptotes occur at the x values for any factors that you are unable to fully cancel from the denominator. Vertical asymptotes occur at x values that make factors in the denominator 0 for factors that you cannot fully cancel from the denominator. Wholes occur when you have factors in the denominator that you could make 0, but it turns out you are able to fully cancel this factor from the denominator. So wholes, you are able to fully cancel those factors from the denominator. These points, these are where vertical asymptotes and wholes become different things. So please feel free to come back to this video, jump to the end, just pause it as often as you need, and just look over these details and what your answer should look like on tests and homework anytime you need.